So just to summarize what we've just gone through, right? Even a biological neuron uh, is a very complex computational machine. So there's an entire field of dendritic computation that tries to understand how neurons themselves integrate information and then integrate information so that they can then start to fire. Now you can also see how, in terms of biological machinery, this is just incredibly complex because it spans so many different time scales. Different types of neurons have different shapes of dendritic trees. So there's a lot of complexity there that we're taking out. And the idea here is if we only take a weighted summation of a set of inputs without any regard for this complexity, we can still capture what the neuron is doing in terms of pattern recognition, right? In terms of this classification that our model neuron is doing. And I think what this highlights is that what this is a testament to how modeling can actually give us something, right? It can be a very, very valuable exercise to try to create a model, in this case, the perceptron, because you get a much clearer picture on what exactly is it that is the core functionality of the thing that I'm trying to understand. And it could have well been that this biological complexity was, certain parts of this biological complexity were necessary to, do this pattern recognition, but it turns out that it's not. And what I want to do now is take that very, very simple model of the perceptron and just look around to see what it can do. So what are the types of functions that this perceptron can do? And we're going to start out with like a very, very simple perceptron even, and see what it can do in terms of classification. And so what we're going to do is we're going to explore around this perceptron model, this very simple model. And what we're going to do is a very simple task. We're going to say, based on a few inputs, we're going to say this thing is a tiger. And we're going to base ourselves on two specific properties or characteristics of input. One is we have a stripe detector. So that's great. We have a stripe detector, which means that we have information about whether a tiger is present because we're detecting stripes, the occurrence of stripes. The other is that a tiger roars. So another one of our detectors is a roar detector. Now, this means our tiger detecting perceptron has two separate inputs, which will, in similarity to what we've done before, are going to call x. So this is a 2 vector of x1 and x2. And those are our inputs. And we're going to have a weight vector also, W0, and then W1 and W2 that correspond to x1 and x2. So what this means is these inputs, they reflect the incoming information of our two tiger characteristics. So stripes detected, our first sort of sensory input, is x1, and it's going to be, if there's stripes, it's going to say 1, and if it says 0, it means that no stripes are detected. And the second is x2, which is 1 if there's roaring that's detected, and 0 if no roaring was detected. So we're going to now formulate our first simple decision rule. If either stripes or roaring are detected, we're going to run. So our output will be 1 for running. And if it's 0, we're just going to stay. Yeah. So let's spell out that decision rule, right? So it's an either or decision rule based on two separate outputs. So if weight 1 times x1 plus weight 2 times x2 are greater than our decision boundary, theta, we're going to say 1, and otherwise, we're going to say 0, right? So this is that weighted summation comparison to some threshold. That's what we're doing here. Yeah? And of course, what this amounts to is that we can take that theta to the other side, and we're just going to say theta, we're going to rewrite as W0. That was part of our weight vector, and that will always get the input -1. So that's just our rewriting. We're just going to append a -1 to the x vector of inputs. That's always there. And that allows us to change, in effect, the theta, the threshold. Yeah, so that's how these two combine. Now, of course, what that then means is if we can rewrite this as a dot product, then it just becomes Wx, right? So that's then a dot product. If that's greater than 0, we're going to run. And if it's not greater than 0, we're not going to run. So let's explore this in. So the reason that I've taken this very, very simple example is because everything can be easily laid out right in front of us, and we can really start to capture the basic computational principles that this perceptron can do. So we're going to explore this perceptron based on this Boolean OR function that the perceptron is implementing in our case. And this is the truth table here of inputs versus outputs. Yeah. So because this is an OR function, what it means is that when any of the inputs are 1, the output will be 1. That's what this table here signifies. Now, I'm assuming that that's clear. Only if the x's are both 0, our output is going to be stay. Otherwise, we're going to run. We're going to run a lot, I can tell you. Yeah, not as much as Trump has done winning, but you can't have everything. So let's say we have x2. That gets the value of 1, and x1 gets the value of 0. So where are we? We are at this line in our truth table, and that means that we will be running, right? So that one's red. Now we can sort of invert the situation. Now we're going to get x1. I think that was stripes. So now we're going to see something with stripes, but it's not roaring, right? And this one was roaring and not stripes. And of course, now we're going to run too, because, we're just testing one or the other, right? That's the Boolean OR. And of course, if we combine them, then we're also going to run, yeah, which we're just doing that OR function. So what that means is if we look at this in a geometric sense, it means that our decision threshold, our boundary is placed in this two-dimensional plane here. Yeah. And if we then think of the different weights that we need to accomplish this, there are, of course, many different weights that we can use because we can shift this up and down, and that will change our weights. And we can also change the orientation of this line slightly as long as it cuts in between these 3. But we can get the situation if we're going to say W1 is 1 and W2 is also 1. And of course, x0 is -1. That's what we said would happen before. So in this case, theta or W0 is 0.5. So that's what this situation would be. So if we have a truth table and a geometric representation and a schematic that we know the W values for, right? So this gives us a complete overview of what the perceptron is doing in terms of its accumulation and thresholding. Now, we were doing a lot of running, as I just said, and we're going to get tired. We're also going to notice that a lot of the times that we're running, there wasn't actually a tiger. We were making mistakes, and they were such that we found that not everything that roars is a tiger. And we also found that not everything with stripes is a tiger, right? So we were making these types of errors that were making us very tired. So we might change our processing, right? We might change and say, from now on, I will run only when I see both stripes and hear a roar, right? So I'm going to combine them into a Boolean and function. And the question now is, can we set the weights of our perceptron such that we create a Boolean and function? Now let's go through that possibility again with that triplet of truth table, geometric representation, and weights in the perceptron scheme. So now we're sort of making ourselves more conservative, right? We're going to only run if both roaring and stripes are present. So we're going to have a lot more green in our geometric representation also. So let's look at how that pans out. We're going to have green, like we had before, when both x1 and x2, so roaring and stripes, are not present, or 0. Yeah, so we're just going to stay. Yeah, we're not going to run. Yeah. The green and red are a bit ambiguous in this representation, for which I apologize. In any case, if we don't see either stripes or hear roaring, we're going to stay. But the difference now is between the or and the and, of course, that if one of them is the case, in this case, we're going to stay, right? Because we want the combination of the two, which means that if we only see stripes or hear a roar, we're going to stay. We're going to stay green, right? But if we have both x1 and x2 being 1, of course, and it means here that then we're going to run. So in this case, if we're going to think of this as a two-dimensional problem space where we have to draw a boundary between the different conditions or different types of inputs, this is where we put it. And of course, there are many different ways in which we could draw this that would still separate out these points, right? Again, we can change the specific orientation of this line, the separating line, and we can change the exact position as long as it's between the red and the green here. But this allows us to set up the AND operation using a perceptron. And if we look at then what we had to do with the weights in order to get here, it was actually very simple. By changing just W0, by changing just W0, making it 1.5, we shifted this decision boundary up and thereby excluded these points as bases for running. Yeah? So this made our problem go from an or to an and operation. Beautiful, right? One single parameter changed the way that we think about our inputs, and we're not going to be so tired anymore. A silent tiger in this case might still kill us, so that's maybe a downside to this whole and operation, but you get the computational point. So there we are. Now, it turns out that stripes aren't actually the danger. It's the dangerous thing is the roar. So our friend just got mauled by a lion because he or she was applying this and rule. So yeah, that's definitely problematic. It turns out that we want to emphasize the roaring in this case. So how can I emphasize roaring in this perceptron, right? So what I want to do is make sure that I only respond when there's roaring, and I stop caring so much about the lines, about the stripes of the tiger, the putative tiger. So again, what I'm going to do is change W and theta parameters. So that's the W vector. Now to emphasize x2 at the expense of x1. And again, if we're at 0, 0, so at the origin of this two-dimensional space, we're going to not do anything. We are going to do something run, that is, if x2, our x2 detector is activated. We're not going to do anything if we start seeing stripes, but whenever we see a roar with or without stripes, we are going to run. Now, that means that our decision boundary is going to be there in this xy plane, or x1, x2 plane. And again, the location, exact location and orientation are irrelevant for this point. And it turns out that what we can do is change our weights such that we get this solution out, right? So this type of decision can be implemented by the perceptron. So that's neat, right? So we can change, by changing these three values, we've been able to go from an and operation to an or operation to one or the other. And you can easily imagine that you could also change the weight such that you draw the line more horizontally. It's a given, given the fact that you could do this. You just switch the two dimensions of input. Um, so this is just a very, very simple example, right? The perceptron and so forth. Those of you that have been through this in terms of more theoretical principles, this might be boring, but I want to highlight that this can be brought to much higher levels of complexity. So in terms of the perceptron, we can create not a two-dimensional perceptron, but a multi-dimensional perceptron on both ends, on both on the input side as on the output side. So what we could do is set up a situation where we want to do character recognition, where we have something like, what is it, 8 by 8, like 64 different binary inputs. And we want to classify whether something is a letter. So that would be 64 by 26. So all of those connections could happen. Oh, so this is a 10 by 10 image, still 100 inputs. So my 100 inputs are now xi, right? So that it's harder to visualize now. And in the case of letter detection, we would have 26 outputs. But the perceptron, the machinery underpinning this is still the same, even though now our weight matrix, so where we had two weights or three with the sort of intercept weight there before, now we have 2,600 different weights that we want to set. Right? But still, we can do this sort of thing. So in this case, this weight matrix being 26 by 100 would give us indices like 3 for the letter C, and 57 would be the weight from pixel 57 somewhere here in that binary image. Yeah, so we have connections from all pixels to all possible outputs. That's what this perceptron has. And of course, that 2600 is a lot of different weights to set. So the question is, how do we set this? And this is where we get back to this general principle that I've tried to highlight in a couple of earlier lectures also, and that is the idea of gradient descent. So a reinforcement learning agent also performs some class of gradient descent, right? It tries to find the direction in which to change its behavior to optimize reward. If we are fitting our parameters of a function to data, we will also perform things like gradient descent. That is essentially the same thing yet again. Right? So this type of computation we see repeated over and over. Now, in order to highlight how this gradient descent principle would work in a perceptron, and again, as you're going to the practicals, the third practical will show you exactly like the nuts and bolts of how this works. Training a perceptron using gradient descent, so you really can inspect how everything works. I've chosen that approach over doing very complex TensorFlow or PyTorch based training, because I think what I really want to highlight here is just the basic conceptual principles. Now, in order to show you how gradient descent works, I've made some subtle changes to be able to use this gradient descent for training. So like I highlighted before, we want to include theta in the weight vector. So that's always going to have a fixed input x0. And so that's there. What we now want is for our activation function, so that was a step function before, but now it's going to be some sigmoid g of a, where a is the input and g of a is the output. And in this case, it's a very simple sigmoid, but you could also use hyperbolic tangent or something like that. The idea here, though, is that it's a smooth and differentiable function. Now, in order to be able to perform gradient descent, I want to know how wrong I am at each point, right? So in terms of reinforcement learning, we had this prediction error, right? So something, if you get a lot of reward, but you expected nothing, that's a very large positive prediction error. If you expect a large reward, but you get a slightly smaller reward, you get a small negative prediction error, right? So we want to quantify how wrong we are in terms of this situation. And we do that in terms of the mean squared error that we want to minimize. So um, we have a target output that we want to aim for. We know what we expect, right? If I present a T, for example, to my perceptron, I want the T to be coming out. And so what this means is that we're going through a supervised learning situation, right? And we are the supervisor here. We are supervising our model to learn the right decisions. So we're just going to use this mean squared error. So that's the sum of the squareds of the differences between the outputs and the targets, what we want the thing to be. Yeah, so we're really comparing the outputs of the model at every instance to the inputs that we gave. And that allows us to see whether it's performing well. So this mean squared error, we're going to use as our measure. And our goal, of course, is to change the W's so that we minimize this error. And of course, we're going to try to change the W's, the values inside that W vector in the direction of less wrong, right? So of course, we want to improve things. And how do we get there? So this direction, we get from asking ourselves, how does this error change when these weights change for each of the weights? And of course, like I just said before, this error is half of the y minus t squared. The y was this function over the weights times x, right? So this is something that we already knew. And the derivative of e here is then the derivative of that function g of a, and this is why it needed to be differentiable, times y minus t times x. So we can go through this, and this gives us a rule for how we need to update the weights at each connection. So that's for every weight, j and I, right? So of those 2,600 in the problem space that I just described, we want to update that weight. And how do we do that? We do that according to this rule for each input and each exemplar. Input and output. Yeah. So we iterate through j and I. Now let me highlight exactly what the different components of this procedure and of this equation mean. So this is what we have. We're going to update the j and I weights. So these all stand for, every j and I combination stands for a combination for, in the example, between a pixel and a output letter. So we want to, what we're going to do here is tailor that matrix of different possibilities, of different connections. And these updates that we're going to do on each step are going to be proportional to the epsilon here, which is the amount of change that we implement. And we can also call this a learning rate. And we've seen that learning rate before in our reinforcement learning lecture, where it was called alpha. So this is exactly the same parameter. It's also, this update of the weight is also driven by how wrong the output neuron was, right? So that's the output that there was and the target that we expected. You can think of this as the reward prediction error, right? How wrong was it? And then we have the sigmoid function, which tells us how much of a weight change, how much a specific weight change will affect the output. So that's the relation between a change of the weight and a change of the output. And then of course, the xi tells us whether there was any input at all, so whether we should be learning at all. Now, of course, we want to minimize the mean squared error. So we want to put a minus there because the error should go down. Yeah. Now, this whole thing is often also called the delta of J, and this makes this the delta rule. And so it is exactly the same type of process that we're going through here as that we went through in our fitting lecture before and in the reinforcement learning also. And you'll see this come back a bunch of times also in the PDF articles that we're reading on Perusall. These things are all translate to one another because they all sort of implement the same thing, right? You have a desired situation where you want to be, and what this procedure does is it gives you a way of getting there. And it doesn't matter whether you're an agent trying to find the way around some environment. It doesn't matter whether you're wanting to fit a model to some sort of data, or if you want to train a neural network to classify things correctly. All of this is, in essence, the same type of computation. So we have a recipe now, and we'll go through this again in the practical, like I said before. But this is really where we're going to go. We're going to present an input. That's the first part of our recipe, and then compute the output. Y is g of wx. Then we're going to compare that output to compute the error. And so what we can then do based on that error is find the local contribution to that error for each of the nodes in our network. And then we can use that delta and the input xi to update the weight slightly with this learning rate. And this allows us to find the minimum of this error landscape. And you see how this is all exactly the same as what we did with fitting routines. We here can also find a local minimum, for example, right? So this type of procedure will not be able to go over this hump. You can imagine also that if you weren't going to do this, the settings of the input, so the starting values of your training can matter. So same types of principles that we discussed in the fitting routine can also hold in this type of training procedure. So that's how we would train a perceptron, and we're going to go through that in the final practical. So that's one sort of basic thing that I think you should take from this course, right? All of this really depends on the same type of processing. This learning rule is also the backbone of how we train deeper neural networks, and I'll highlight that in the next lecture. And I think after we've treated that, you have the conceptual background to go through all of the different papers that we'll be reading, for example. What I do want to highlight is something other conceptually interesting. It's how neural networks function, exactly what I'll be going into in the next lecture. I want to sort of presage here, and that is that perceptrons have a specific problem. Perceptrons are very nice classifiers. You saw exactly how they worked in these previous slides, but they are fundamentally limited in a very important sense. And I'm already highlighting the situation in which perceptrons run into problems here. If you can look at the truth table on the left, you can already get an idea of the type of situation that this causes problems for. So the problematic situation arises when, if we want to decide to run based on either x1 or x2 being the case, but not on them both. Yeah. So this hints to the specific class of problems that perceptrons cannot solve. That is, for our tiger example, roaring or stripes, but not both. And what this is the Boolean exclusive OR function. And this, for the perceptron, leads to problems. And let me highlight how that works. And I think the easiest demonstration is if we take that geometric representation and just draw this situation. So 0, 0, we stay. 1, 0, 0, 1, in this case, x2 is on the horizontal axis. We run. x1, 1, x2, 0, we also run. But if they're both 1, we stay, right? That's the XOR. And here we have this problem, right? I can only draw a line through these points, and I can draw it like, how am I supposed to draw it, right? I'm at a loss. And specifically, the problem here is that in this situation, the problem is not linearly separable, right? The XOR operation is a nonlinear operation, and this extends to higher dimensions, and it really reveals the perceptron's fundamental shortcoming. Yeah, it cannot do this nonlinear type of problem where the problem space, that this is like the simplest possible example of, cannot be divvied up by a single straight line, because that is the fundamental principle or property of the perceptron that makes it handicapped in this situation. Now, of course, we wouldn't have all this deep learning stuff and all of that if smart people hadn't already thought of a solution. And it's actually a very simple solution. And it, again, takes a part of this knowledge that we have of the biological brain, namely that it has more layers, to find the solution to this problem, which is just to add a hidden layer. So what we can do is we can make a hidden node H that responds to either, and make a hidden node H2 that responds to both. And then what we can do is, because we have this extra layer, we can make an output node that then responds to H1 and not to H2. And we have just solved our problem. So this extra layer, what it does is it allows us to reflect the sort of duplicate and fold over the problem space, so that these two situations occur at exactly the same point, and then we can draw a straight line, right? So the property of the perceptron is still that it only draws a straight line, but now we've been able to warp that problem space such that the two situations for which we would or would not want to respond end up in the same location, and that allows us to draw that straight line. And this is a really, really powerful approach, because this extra layer allows us to perform all sorts of nonlinear combinations. And just to highlight that power, I want to show you exactly the same type of situation, but an alternative configuration that you see on the left bottom here of that same network, just with different weights. So now it's configured differently. And what we can do is we can make a hidden node H1 that responds to X1 and not X2. And we can make a hidden node H2 that responds to X2 and not H1. And then we can make an output node that responds to either H1 or H2. And I invite you to really go through both of these examples, and we will highlight them more deeply in the practical. But again, what we see is what the extra layer has done is it sort of folded over the problem space so that we can start drawing a line there. What I want to Yeah, so I hope this sort of gives you an idea for the shortcomings of the perceptron and how adding layers makes this a stronger and more versatile classifying machine. And you can already see that here we have the starting point of the idea of making more and deeper networks, right? Because this is what gives these networks their versatility. In fact, multi-layer networks like these can solve everything. And you're going to go like, huh? Everything? I don't believe that. But the point is, if you go into computational theory, it's true. You know, this statement has no catch. These models can solve everything, and it's because multi-layer networks are universal function approximators. So not just for classification, it is, you know, mathematically a fact that these multi-layer networks can solve any mathematical function. So there's no problem that these cannot solve. Right? They are universal function approximators. But you can imagine that if I have a complex problem, I will need an equally or more complex neural network to solve the problem, right? And that really shifts our problems to now having to find the right configuration. What I want to show you guys, and I really want to invite you to have a look at this. There's a really nice website at this URL. I really want to invite you to go there. It's also it's in the PDF on the in the lectures on Canvas, so you can click on it and go there. I just want to show you an example of what that looks like, because this really highlights this idea of being able to of linear separability and that sort of thing. So what I want to do is go to that website and just show you how it works, because it's a really nice way of tinkering with these little neural networks. Can everybody see this? Okay, so this is a neural network tinkerer. Um, it's all put in, it's all programmed up in JavaScript, so it's very easy to work with and run in your browser. It's the entire thing runs in your browser. So what I'm going to do is have 0 hidden layers. Yeah, so I just created a perceptron and I just deleted all the hidden layers in the middle. And I created a problem space that is, as you see, should be linearly separable. So let me just regenerate this. Let me see if I can train this neural network to find the solution and correctly classify these different populations, right? The orange and the blue population, as you see here. So you see, you didn't even see it. It was too fast. Let me see. I want to add some noise. So I want to make sure that they overlap a bit. And let's see. So now we're going to see this model learn learn to make the right decisions, and the underlying decision sort of manifold is what you see in the colors behind, and the data are just the dots here. So let's just rerun the training, and you see, it immediately finds it. See that? So you go from this naive situation with random weights, and just regenerate the problem, rerun, go back, rerun. It finds it immediately, right? It finds this difference immediately. If I add more noise, perhaps it will take more time. You see, it's a very simple problem for this perceptron to learn. Yeah, but there are multiple problem spaces that I can have a look at here. So one of them is this one. And this is exactly that XOR problem that I showed you before. You see how that works? There's a blue cluster here, a blue cluster there, orange cluster here, orange cluster there. So can I solve this problem with these different, with this perceptron without a single hidden layer in the middle? So what I can do is try and fail. So here you see, I'm gonna fail. Now, maybe this was due to the fact that I had a lot of noise in here. So I'm just going to decrease the noise, and you see that the overlap between these different distributions decreases. And let's run it again, right? Oh, you see it learns a bit, but nothing. Yeah, there's still like almost grayish, right? It just hasn't learned to find the right solution. I can rerun this over and over again. There will not be a solution for this situation. Now, this website has a bunch of other different types of data sets that you can work with, that you can try out. I'm going to stick with this XOR problem because let's see, I can try to maybe add more features. Well, like here maybe. I don't know. These are already very complicated features. So I can add different features. I'm not going to do that. So what I think I've shown you now is you cannot solve this problem with these two x1, x2 inputs, right? So I can do transformations on the inputs, and that allows me to solve the problem more flexibly. What I want to talk about is adding hidden layers. So what I'm going to do now is add these two neurons, a hidden layer, and see if I can find the solution to this problem if I start training it. So here we go. And you see it's trying to find this thing here. And it sort of depends on where you start out, whether it will find the optimum. And you already see that it's trying to do much more than it did before, right? So you're it's doing something, and it's already at a level where it's a lot better than it was before. Now, I think we're sort of stuck in this episode. So what we can do is add another layer, right? Just to show you how adding more and more layers will make this more flexible. Let's see where it goes. And you see that it has more leeway to work with this, but still it's stuck in the same situation. And what I want to do is, so if we want to regenerate this and try again, you see that it is starting to do something, right? It's able to now draw a boundary here, making it perform a lot better than it was before. So really depending again on the initial situation of the weights and on the exact data. But let's try to make it more flexible again. Whoop. By adding a few neurons to the intermediate hidden layers. And you will start to see that this network will be able to twist around its boundaries to actually perform really well, right? So you see, what did we need to be able to fit this type of, oh, there we go again. What we needed to perform this type of problem separation really hinged on adding extra layers. So this is sort of, it kind of depends on how you want to run it, but you see that adding one extra hidden layer actually already gives you the type of flexibility that you need to do this XOR type thing. So what I think this gives you, this website, I really want to advocate you playing around with it a bit, because you really see what do you need for a network to be able to perform this type of XOR operation, and how is that a function of the amount of hidden layers, the amount of hidden neurons, and the sort of shapes of the input neurons. So this will definitely give you a way of building some intuition for how that works.